Hi, welcome to Chapter 9, Overview Part 5, where we're going to talk about polarity. So, let's review what polarity means. First of all, what is electronegativity? Electronegativity is the ability of an atom within a molecule to attract an electron to itself. So the higher your electronegativity, the more it attracts an electron. What is the trend for electronegativity? So as you go across a period, it increases. As you go down, it decreases. How is electronegativity related to the polarity of a bond? Well, if you subtract the electronegativity between the two atoms that are bonded to each other, if you get a large difference, then the bond is polar. And a kind of rough estimate to once you subtract your electronegativity values, you could see if they're close to zero, it's nonpolar. If you're moderate, you're polar, and then if you're extreme, you're ionic, because at this point you're stealing an electron, you're not even sharing it anymore. So electronegativity and polar covalent bonds. When two atoms share an electron unequally, that is called a polar covalent bond. And electrons tend to spend more time around one of the atoms, and the one that the electron is spending more time around will have a partially negative charge on it. So then you will develop something called the dipole, where the arrow points to the element that has the electron spending more time around it. So if a bond in a molecule, if the bonds in a molecule are polar, does that mean the molecule has to be polar? And the answer to that is actually no, not necessarily. So just because you have a molecule that has polar bonds does not mean that the molecule as a whole will be polar. You have to look at the dipoles and see if they cancel each other out. So in carbon dioxide, you have polar bonds, and these are your dipoles. If the arrows are the same length, same magnitude, but pointing in opposite directions, they cancel each other out. So this is nonpolar. Let's take water. Here are our dipoles. They're pointing towards oxygen because that's where the electron likes to spend most of its time. They're the same length, but they do not cancel each other out. And your overall dipole will be pointing up like this. So this is a polar. So by adding the individual bond dipoles, you can determine if the molecule itself is polar or not. So there's a couple of questions you need to ask yourself. First of all, are you covalent or ionic? If it's covalent, are the bonds polar? Do they have a bond dipole? No, then the molecule most likely is nonpolar. Yes, then do the average positions of your delta, your partial positives and your partial negatives, do they coincide? Is there an overall dipole moment? And is that equal to zero? If it's equal to zero, that means they cancel each other out. So then your molecule is nonpolar. If they're not equal to zero, then you have a polar molecule. If you have a center atom and you have different atoms attached to it, most likely it will be polar because each of those atoms have a different polarity. The bond polarity is different. So let's compare two molecules. So here we have carbon dioxide, which I already said is nonpolar because the dipoles are canceling each other out. Here you have water. The dipoles do not cancel each other out. You end up with the overall dipole moment facing upward like this. So this is polar. Here are some examples of polar and nonpolar molecules. Here your bond itself is polar and it's a linear molecule, so it is polar. Here, each of these bonds are polar, but they are symmetric around the center atom, so they end up canceling each other out. So the molecule itself is nonpolar. Same thing happens with tetrahedral. As long as these four atoms are the same, then these dipoles will cancel each other out, and it's nonpolar. Over here now, there's a lone pair sitting up here, right? So the dipoles are not going to cancel each other out, so it is polar. This is tetrahedral again, but this is not, you have 3 hydrogens and a chlorine, so you're going to have an overall dipole moment, so it's polar. And I read this in the book and I thought it was pretty important, so I put it over here. So if you have molecules that are nonpolar, when the center atom is symmetrically surrounded by identical atoms, that's what's happening here. Nonpolar. The center atom is surrounded by identical atoms. For A, B, N, so that general formula for a molecule, in which all the B atoms are the same, certain symmetrical shapes will be nonpolar. So a linear one, so that was carbon dioxide, right? That was nonpolar. Trigonal planar, this is trigonal planar right here. Tetrahedral, this is tetrahedral. Square planar. A square planar is when you have 6 domains, but 2 of them are lone pairs. Trigonal bipyramidal, so that's your 5 domain guy. And octahedral, which is also your 6 domain guy with all bonds. These will always give you a nonpolar molecule if B is the same in all of them. So let's practice a little bit. So let's draw the Lewis structures, determine the shapes, and then draw the dipole moment. So it is kind of important when you draw your Lewis structures to draw them in the right shape. So this is bent. And oxygen is more electronegative, so you draw your arrows pointing towards oxygen. So your overall dipole moment will be going up, and this is polar. CH4, I'm trying to draw it to look tetrahedral. The shape is tetrahedral. And all of the dipoles cancel each other out, so this is nonpolar. It's very symmetric. NO3 has 3 domains, so this is trigonal planar, and it's bonded to 3 oxygens, so this is nonpolar. The dipoles will cancel each other out. Ozone. Ozone's kind of tricky because you would think, since they're all oxygen, their electronegativity differences would be 0 and it would be nonpolar. But actually what happens is, since it is bent, and you have a pair of lone pairs here and you have nothing here, you're not symmetric. So you will actually have a dipole moment. And as it turns out, it'll point away from the lone pairs. So this is polar. Well, that is it for part 4.